Okay. Are there any questions so far? No? Okay. We'll now move on to the next module, which is on matrix inverses. Okay. So here we will look at, we algebraically know what a matrix inverse is, inverse of a matrix is. For example, if I have a matrix A, I have a matrix A, and I tell you that B is an inverse of this matrix. If I say that you know that, what all do you know about A? If I say A is a matrix and B is its inverse, right? Okay, then what all can you say about A so far? So from whatever we've learned so far. Square, yes, good. Square. Another important one. When does a matrix have an inverse? Square matrix, huh? No, identity matrix. Yes, identity matrix has an inverse. It's identity matrix itself. Are you saying only identity matrices have inverses? Must be full rank. That means the rank, if this is an n cross n matrix, then the rank of the matrix A must be n. Only then it has an inverse. And I know that if B is an inverse, then BA equals IN, and AB equals IN, and we generally represent this by, this is also an n cross n matrix, and it's also full rank. That means A is the inverse of A inverse. Okay, so inverse of A inverse. See, all this we know. We know the algebra so far, right? But a big thing for us in this course has been connecting geometry and algebra. Right. The next question is, okay, do matrix inverses have an interesting geometry associated with that? Before we look at that, let's go back to an idea that we discussed earlier. And it's happening. So we're talking about R2. Okay, so this region is the space R2, right? And we usually choose an arbitrary point as the origin, and we define that to be the zero vector. Right? Now let's say we have a point here. We can associate that point with a vector. Okay? That will be this vector. Okay? Let's say I call that vector X. So whenever I'm talking about this vector X, then I'm essentially talking about this point. Right? That point is fixed in space. Right? That point is that point, right? That point in space. But whenever we want to represent that point with numbers, right? We need a reference to assign numbers. Okay? Right? For example, let's say I have a mass. Right? Some object, it has some mass m. I don't know the value. The moment you assign a numerical value to that, or if you want to assign a numerical value to the mass of that object, you need to have a reference. Right? For example, I could be using the standard kilogram as my reference, and I could say, well, the mass of this object is 0.1345 kilograms. Right? So to assign a number to that quantity that you were talking about, the mass exists independent of us assigning a number. Mass is the mass of the object. But the moment you say, I want to assign a number to that quantity, that variable or that entity, you need to have a reference. Right? In the scalar case, it's usually some standard that we use for assigning that number. Could be grams, if kilograms, or you could be using grams, or you could be using pounds. Right? Depending on what reference you use or scale you use, the number that you assign for the mass of the object will be different, even though all of them are referring to the same reality, the mass of the object. Right? The same idea extends to higher dimensions. Here we are only dealing with one number, a scalar, R1. Right? So then the mass, so here the mass of all possible objects in the universe are represented by R1, the space R1. Well, not necessarily R1, we don't have negative masses, but at least they are a subset of R1. Now, if you're talking about more than one number, then we're talking about R2, R3, Rn, and stuff like that, right? So now, and for a place where we would use R2 is, for example, to represent this point in space. They said that point is that point in space, right? That's fixed. Now, what number you assign to that point depends on, again, what reference or scale that you use. The reference scale that we're talking about in R2 and higher is essentially what is called the numbers that you'll assign to this x vector. The x vector could you could obtain any number, you could use any number you want depending on what reference you use. For example, let's say we choose these two. I choose two vectors, A1, A2, as my basis vectors. And let's assume for now they're orthogonal. Right? And let's assume also that both are of length 1. So A1, 0, A1, and both of them have length 1. Okay? And if I wanted to represent the vector x using numbers with A1 and A2 as my reference, as my basis, how would I obtain that number? So what I mean by that is this. I want to be able to represent x in terms of A1 and A2. And I want to do that using two numbers. And I can do that by doing this. Right? So here, if all of us agree that we're going to work only with the A1, A2 basis, okay, then for me to convey information about this point x, all I would have to give you are the numbers alpha 1 and alpha 2. Because all of us have agreed to use A1 and A2. If I give you alpha 1 and alpha 2, you know exactly where x is. Right? Because all you'll have to do is scale A1 by alpha 1 times, scale A2 by alpha 2 times, and then simply add them, and then you'll get to the point x. Right? Similarly here, if all of us agreed that we were only going to use a kilogram scale, then I can simply say the weight is 0.15. And you know exactly how much that is, because you know what 1 kilogram is. Right? So once we agree that we're going to be working with a fixed basis, both of us, then all I need to tell you to convey information about any vector in R2 or Rn for that matter are these scalars. Alpha, in the case of R2, only two scalars, alpha 1 and alpha 2. Okay, that's great. Okay, I hope that's at least intuitively clear so far. Right? Okay. Now the question is, how do we find alpha 1 and alpha 2? Let's say we've agreed this is the space, we've agreed this is A1, this is A2, and I tell you we need this point. I need to convey information about this point to you guys. You cannot see this. How do I find out alpha 1 and alpha 2 given these bases and my vector x? Geometrically, I'm not asking algebraically. Well, you already know this. You've done this since the 11th standard. Sorry? Sorry? That's all, yes. What would you normally do if this was a problem in physics and they asked you, well, in physics, we might have said, well, this is the x-axis, this is the y-axis, and you might be asked, what is the x component of this vector or the y component of this vector? So here, another way to think of alpha 1 and alpha 2 is alpha 1 is the A1 component of X, alpha 2 is the A2 component of X. So I'm asking you, how do we find the A1 and A2 components of this vector X? And what he said is correct. All you do, well, the way you would have done it in a problem in physics or in vector algebra is this. So you go to the point tip of the vector X, you drop a perpendicular onto A1, and then you find out this distance. Just use a scale and measure the distance. Drop a perpendicular onto A2, and then you measure this distance. If both these intersections, so you measure the distance, of course, right? That's a positive. Distance is always a positive number, but you will give it a sign depending on where these perpendiculars intersect with the A1 axis and the A2 axis. Right? For example, if the vector was here and the intersection, when you dropped a perpendicular onto A1, if it intersected to the left of the direction in which A1 is pointing, then you would assign a negative number to that, right? So that's how you do it geometrically. Okay. So once you do this, now this will be alpha 1, this will be alpha 2. Now if I give you alpha 1 and alpha 2, you have A1 and A2. All you will do is you'll take A1 and then stretch it by alpha 1 times, bring it here. You'll take A2, stretch it by alpha 2 times, bring it here, and then just add these two vectors. That will get you to X. Right. That way, once I give you alpha 1 and alpha 2, you know exactly which point I'm talking about. It means this vector X now, the representation of this vector X in the A1, A2 basis is essentially okay. And any time we assign numbers to a vector, right, there is always a basis associated with it. So far, you might have seen me just write stuff like this, saying a vector. Right? Because I've assigned numbers, that means there is a basis that I've kind of assumed that I've just not explicitly spoken about. Okay? So that's something you should remember. Anytime you assign numbers, there is a basis reference that you're using. We already saw in the first module, if you had an orthonormal, so here A1 and A2 is an orthonormal basis or no? Is A1, A2, so this set A1, A2, is this an orthonormal basis? What is an orthonormal basis? Or what is the basis? Let's start there. Sorry? No, basis. Let's start with basis. It's a linearly independent set. Span what? No, it spans what? Span of what? It's a linearly independent set that spans the vector space that we are interested in. Okay, then we say it's a basis for that vector space. If it's orthonormal, then the individual vectors will have length 1, measured at least by the 2 norm, or length 1 measured by the 2 norm, and their standard inner product is 0. They are orthogonal to each other. When you have an orthonormal basis, how do we find alpha 1 and alpha 2 algebraically? If you remember from module 1, an advantage of the orthonormal basis is that it's actually relatively easy to find out alpha 1 and alpha 2. If you take the inner product of the left hand side and the right hand side with A1, okay, what will you get? You can take this inside. So you'll have alpha 1, A1 transpose A1 plus alpha 2, A1 transpose A2. And what is that equal to? Yep. What is it? Huh? That's equal to alpha 1. Because this will compute to 1. What will this compute to? 0, because they're orthogonal to each other. In fact, this says that your alpha 1 is simply the standard inner product of x with A1. That is exactly this operation. The standard inner product of x with any vector A1 is you simply drop a perpendicular onto that line, onto that vector A1, and then see where it intersects. And this distance that you get will be alpha 1. So in fact, here alpha 1 is equal to A1 transpose x. Similarly, what is alpha 2? That will be E2 transpose x. So here this will be okay. Okay, all right. Now let's generalize, right? Let's say we are dealing with Rn. Okay? Let's say we have a basis, just a basis. We don't know that if it's special, if it's not, if it's orthonormal. We just know it's a basis, and the basis vectors are v1 to vn, and we have another vector b. Okay? We can find the representation of b in the v basis. I'm going to call this the v basis. Okay? When we say, for example, let's say I tell you, well, the representation of the vector b in the basis v is beta 1, beta 2, beta n. If I tell you that, what does that mean? Well, it means this. Well, I've written it as vi, but that's okay. I've written it as ai, but here. This means I can write b as beta 1 times v1, beta 2 times v2, beta n times vn. That's what that means, right? Each of the numbers tells me how much do I scale the individual basis vectors and then add them so that I get this vector b that we are talking about. Right? That means b can be represented as a linear. So b can be represented as the linear combination of the basis vectors v, and the exact mixture for the linear combination is given by the betas, which is actually the representation of the vector in that basis. Okay? A linear combination of a set of vectors can be written as a matrix multiplication operation involving a matrix and a column vector, right? Post multiplied by a column vector, right? That means if I get my basis vectors, right, and then I form a matrix V, where the columns of the matrix are the basis vectors themselves. V1, V2, Vn. What will be this shape of A? Sorry, V. Sorry. Okay. Each of the vectors V. What is the shape of Vi? Is that a scalar or a column or a vector? Well, this set forms a basis for Rn, That means the individual elements have to be vectors from Rn. That means this is Rn. So that means what will be the shape of this? It will be n cross n, right? Means, and let's say I take beta and I write it as beta 1, beta 2. And this is another vector from Rn. Okay. Means now, and I know B is from Rn, and I know that the relationship between beta 1 to beta n and V is given by this. That means I can write beta as matrix V multiplied by beta V1, V2, Vn multiplied by beta 1, beta n. A matrix post multiplied by a column vector, which is, that means you're taking the linear combination of the columns of the matrix, and the mixture for the linear combination is given by the scalars of the components of the of the column vector, which will be beta 1, v1, v2. Okay. That means if we are given a vector b and a basis set, right, which essentially means we know the matrix V, and our goal is to find out beta. That means we are essentially asking what is the representation of the vector B in the V basis, right? That question essentially translates to solving a set of linear equations, right? Because this is equivalent to X equals B, where A is V, X is beta, and B is V, right? And we know the matrix V is a square. Is it full rank? If it's S, yes. Why? If it's no, why? Sorry, why? Yeah. It's full rank because it's got all the columns are linearly independent. There are n columns. Okay, so it's a square full rank matrix. That means its inverse exists, right? V inverse. And if I know V inverse, that means I can obtain beta. That means beta is essentially given by okay. Now we can assign give the inverse of a matrix a very specific meaning. What is the role of V inverse here? The question we initially had was, how do I find the representation of my vector B in the V basis? Here we are saying, well, that representation is given by V inverse multiplied by your original matrix B. So what is the role of V inverse there? Well, V inverse essentially plays the role of finding the representation of a matrix of a vector B in a basis which are essentially the columns of the original matrix V. Okay, the bases that we're dealing with are the columns of V. If you want to find the representation of any vector B in this basis, all you do is take V inverse and post multiplied by B, and then you'll get. So one way to think about A inverse is find representation of vectors basis. Which basis depends on what were the columns of the original matrix that you're talking about. Okay. We have this. So the representation is given by V inverse. If you're talking about a matrix, right? Or here, you're talking about computing V inverse. That means you have a matrix V that you have that you're using, and this matrix itself is represented by a bunch of numbers. In fact, the columns are all the individual basis vectors. That means each of this basis vector itself is represented by numbers. But earlier I just told you, well, anytime you assign numbers to a vector, you're implicitly using a basis. Then you should ask, well, what basis were the original vectors represented in? Is it clear? Or, well, numbers to vectors always requires a basis. And then I just very casually told you, well, if you have a set of basis vectors like this, you put them into a matrix like this, and then compute the inverse of that matrix, and then you'll get the representation of B in the V basis. But I conveniently did not say anything about what basis the original vectors were represented in. Okay. So whenever you have something represented with numbers, a vector represented in numbers, the basis is usually clear from the context in which you're talking, in which you're discussing things. If nothing is mentioned, you simply assume that it's in a standard basis. And the standard basis is essentially E1, E2, En. Okay. So our original basis vectors V1 to Vn were represented in the standard basis. Okay. But now we had another matrix basis that we were interested in, which was the V1 to Vn basis, which is the V basis. Right? And this operation here essentially allows you to convert from the representation of the vector B, which was originally in the standard basis, to the new basis, which is the V basis. Okay? So one way to think about the inverse of a matrix is that A inverse is the matrix that allows change of basis to the columns of A from the standard basis. I've been using V, but essentially A inverse. So the meaning of A inverse is that it essentially is a change of basis operation. Okay, so whenever in a complicated formula you see an A inverse, one way to interpret that operation is some basis change operation is happening. That means you're essentially taking something and looking at it from a different perspective. That's all. Okay. Right, so we'll dig a little deeper into this. Let's go back to our example here. So here we were considering an orthonormal basis. Right? But the discussion we just had about using A inverse as a general basis change operation should be applicable for this also, right? Because an orthonormal basis is a basis. Right? But in this particular case, we said we can easily compute alpha 1 and alpha 2 by simply doing this operation. Now the question is, are the two statements compatible then? is, does A inverse essentially become this operation when you have an orthonormal basis? Is it clear? So let's look at that. Right? Let's say we did not know that A1 and A2 formed an orthonormal basis. Let's assume it was just some basis. And I asked you, well, can you convert X to the A basis? Okay. Then what you would have done is you would have formed a matrix A with A1 and A2 as its columns. This will be a 2 cross 2 matrix, okay, because we're dealing with the R2 and there are two vectors. The matrix is invertible because it's square, and it's full rank because A1 and A2 form a basis for R2. That means it has a full set of linearly independent columns. That means the rank is n. Rank is 2. That means it is invertible. That means now I can find my the representation of my vector x. If I take if I take my matrix A, take its inverse, and multiply it by x, then I'll get y. Y is the representation of x in the A base. Okay. So we need to do this A inverse operation. But now, if we know that the basis is actually orthonormal, okay, what do we know about the matrix A? The matrix A is not any arbitrary matrix. It's got a special property now, or it's got a special name. If the columns are orthonormal. You remember? Becomes an orthogonal matrix. Okay. What is the special property of orthogonal matrices? There is something special about their inverses. What is the inverse of an orthogonal matrix? The inverse of an orthogonal matrix is simply A transpose. Okay. Okay. All right. Now let's see. We are saying Y, which is given by alpha 1, alpha 2. Here. Alpha 1, alpha 2. Okay. Is given by A inverse X. Okay. But A is an orthogonal matrix. That means A inverse is simply A transpose. Okay. If A is this, what is A transpose? What will A transpose be? Well, how do you do the block transpose operation? Sorry. Column? Column turns to a row. Yes. Okay. No, I'm asking. Here A is represented as a block row. So what will be its transpose? Okay. This will be A1 transpose. Sorry. A2 transpose. Okay. You can verify that this is still 2 cross 2. Okay. That means my A transpose is A1 transpose, A2 transpose by X. Well, this is a 2 cross 2 matrix multiplied by a 2 cross 1 vector. That means I'll get a 2 cross 1 vector. And the first element of that vector will simply be the inner product of the first row of the matrix with the column. Second element will be inner product of the second row with the column. The inner product of the first row with the vector is the product of the second row. That's essentially equal to, okay, that's what we had here. Okay, that's what we said we should do geometrically. Okay, so the point I'm trying to make is that yes, the A inverse of the inverse operation. That's essentially, you can think of that matrix as a basis change or matrix that allows you to change from one basis to another, or the standard basis to the basis represented by the columns of the original matrix. Right. So that's all I wanted to say about inverses of square matrices. And so far, we've talked about inverses only in the context of square matrices. And we said inverses are only defined for matrices that are square and that are full rank. And whenever you have a full rank square matrix, we said there is a unique inverse such that if you do A inverse A, it will be equal to A inverse, and you'll get IN. Okay? So it doesn't matter whether you pre or post multiply the inverse with the original matrix, you'll always get the identity matrix. Now you could ask, well, okay, is it possible? And here, is it possible that I have a matrix A, and if I pre-multiply it by something, I get I, but if I post-multiply, I don't get I. Similarly, you could ask if I have a matrix A, if I post-multiply by a matrix, I get I, but if I pre-multiply, I don't get I. Okay? It turns out this is possible. Okay? And this happens whenever you don't have a square matrix. The matrix has to still be full rank. Okay, but if it's not square, then if it's not square and if it's full rank, then only one of these will be true for that matrix. Either the first one will be true, that means you pre-multiply by a matrix and you get I, and post-multiply you don't get I, or you have post-multiply and you get I, and you pre-multiply you don't get I. Okay, whenever that happens, so in this case, right, here we say the matrix A only has a left inverse because B is to the left of A. And in this case, we say A only has a right inverse. When the matrix is square and full rank, it has both a right inverse and a left inverse, and both of them are the same. A inverse here. This means if this is equal to I, that means A inverse is the left inverse of A. If A inverse equals I, that means A inverse is a right inverse of A. That happens only when the matrix is square. Okay? So now we look at essentially talk a little bit about left and right inverse. Maybe before we go there, maybe we'll do one or two numerical examples with basis change. Okay. Let's say we have A1. Okay. And I have a vector B. So here I put down numbers without saying what basis. So you assume it's in the standard basis. Now I ask you, what is the representation of B? I'm going to write it like this. This means the representation of B in the A basis. How do we find this out? Well, we know how to find this out. You take A inverse and multiply it by B. What is A? First, well, to compute A inverse, we need to know what is A. What is A here? Sorry? Okay. Is it 1, 1 minus? Oh, horizontally. Yes, yeah. That's all. What is A inverse? Well, you can either go about computing A inverse, or you can first check if the columns are orthonormal. If they're orthonormal, you can just take the transverse, that's A inverse. That's the columns orthonormal. You don't have to stare, you can simply compute. Are the lengths one? Are they orthogonal to each other? Yeah. Yes or no? They're not. What condition do they fail? Length is not one. Did you compute it or? Okay, then this one. Okay. Are they orthogonal? Yes or no? Dude. How do you compute if they're orthogonal? No? Yeah. Yes. Okay. Do the inner product. What is it? Is it 0? Okay. All right. So it's It's an orthonormal basis. Then what is the inverse? Well, if the columns are orthonormal, that means it's an orthogonal matrix. Orthogonal for the orthogonal matrix, A inverse is A transpose. That will be it's simple. That means it'll simply be 1 minus 1, 1, 1. That's the inverse. Okay. So now we know how to find out A is 1 by root 2, 1 minus 1, 1, 1. B is minus 3, 4. That means have minus 7 and 1. Okay, so that's the representation of the vector B in the A basis. And you can verify this, that we know that if this is correct, then BA should be minus 7 by root 2 times A1 plus 1 by root 2 times A2. A1 is minus 7 by root 2 times 1 minus 1 into 1 by root 2. A1 has a 1 by root 2, right? Plus 1 by root 2 multiplied by 1 by root 2, 1, 1, means I get minus 7 by 2, 1 minus 1, plus 1 by 2, 1, 1. So I get minus, I'll take the half outside. This will be minus 7 plus 1. This will be plus 7 plus 1. Be 1 by 2, minus 6, 8. That is your B. Okay. Now, let's do the same thing. except now we choose a different set of bases. Do the vectors A1 and A2, do they form a basis for R2? The new vectors written in red. Again, if you say yes, you'll have to tell me why. If you say it's no, you'll have to explain why. What are the two things you need to verify to check if something is a basis? Linear independence. It must span. Okay. If a set of two vectors are linearly independent, it will span R2. So only thing we have to check is, are they linearly independent? Are they linearly independent? How will you check if two vectors are linearly independent? Sorry? Yeah, go ahead. Correct. But if you only have two vectors, it's kind of, the problem is kind of easy, right? They should not be collinear. If they're collinear, that means one will be a scaled version of the other. Are, look at these two. Are they scaled versions of each other? Is there a single number that you can, is there a single number alpha such that if you multiply A1 by alpha, you'll get A2? No, there is no alpha that will satisfy where minus 2 alpha is 1 and alpha equals 4. So that means they are not linearly independent. Sorry, they are linearly independent. They're not linearly dependent. That means this A1 and A2 does form a basis. Are they orthonormal? So do A1 and A2, do they form an orthonormal basis for R2? Yeah. What conditions do they fail? Length is 1? Okay, length is not 1. Are they orthogonal? No, they are not. Okay, so this is not an orthonormal basis. So if I form a matrix A, will be minus 2, 1, 1, 4. I cannot simply take the transpose to find the inverse. I have to do the work to find the inverse. We've never really talked about how to find the inverse of a matrix. Um, one procedure to find the inverse of a matrix. So we look at one procedure now. Let's forget about the inverse for now, right? Let's say I want to solve for this matrix for some specific B. Sorry, I should not use B. I'm going to use Y. Okay. First, we know how to solve linear equations. We've seen that. Solve this and tell me what will be, I'm going to call it x1. Tell me what is x1. That means I'm essentially solving for minus 2, 1, 4 multiplied by x1 will give me E1. What is E1? Yes. I'm saying use Gaussian elimination, solve it and tell me what is x1. Should not take so much time. No, you got it? No, you're not sure how to solve? No? Dude, if you have the solution, tell me. We'll verify whether it's right or wrong. Or if you don't know how to solve, tell me. I will do it. Because if you keep quiet, I don't know what is going on. Would you like me to solve it? You have the answer? No, you don't. Okay. So you're not able to solve it. Okay. To do Gaussian elimination, we first what? Choose a pivot and then make everything below the pivot 0, right? And we essentially do the same operation to B as well. -2, 1, 1, 4. Right? Well, the pivot is not 0, so we don't have to do any row exchanges. We have to make, so the pivot is this. We have to make everything below the pivot 0. That means you need to make this 1, 0 by essentially scaling row 1 and adding a scaled version of row 1 to row 2. Row 1 remains the same. 1. If I multiply the first row by half and add it to the second row, this will become 0. If I multiply this by half and add it to 4, it will be 4 plus half, which will be 9 by 2. Okay. I multiply this by half and add it to this, which will be half. That's all. The purpose of Gaussian elimination is to get the matrix to an upper triangular form. That means now we've already got the upper triangular form. That means the new system of equations is essentially this. -2, 1, 0, 9 by 2. I'm going to call it x11, x12, because I've called the vector x1. So I'm going to call I'm going to call the individual elements with use two subscripts for the individual elements. The modified b is this, which is 1.5. This is easy to solve, right? Because the very last equation has only one unknown. That means x12 should be what? 9 by 2 x12 is half, which means x12 should be 1 by 9. And x12 is 1 by 9, then 2 times x11 plus x12 equals 1 plus 1 by 9 equals 1. Be minus 8 by 9. Like that x11 will be 4 by 9. I think that is correct. You can verify that later. I mean, we'll know very soon. That means x1, I'm going to write x1 here. X1 that I get is 4 by 9 and 1 by 9. Okay? All right. Now, let's do this. You can follow the same procedure and tell me the solution for this equation, where a times x2 is e2. That means -2, 1, 4 times x2 equals 0, 1. Tell me what x2 is. Minus, okay? Where did I do a mistake then? Well, of course, Just plus 1 by 9. That was a mistake. Yes. Sorry. Yeah. Yeah. That's okay. Yeah. Do you have for this one? What is x2? Actually, yeah. No, no, continue. Nothing. Yep. What is it? Minus n by 2. 9. Are you sure? This is definitely not right. This I know. What is it? 1 by 9, 2 by 9. I think that is correct. Okay. So I have x2. Okay. Fine. Now let's say I take these two columns. Okay. And I form a new matrix B. Okay. What will I get if I do AB? Just verify. If you're not able to figure out, let's just do the numerical operation and find out. So this matrix, there is a 1 by 9 that is common. I can take that out. So it's minus 4, 1, 1, 2. So if you multiply these two, that means I can take the 1 by 9 out. This is minus 2, 1, 1, 4 multiplied by minus 4, 1, 1. Sorry, what? Yeah, no problem. Yeah. What do you get? Sorry, identity matrix. Yes, yeah. That's strange. It looks like B is the inverse of A. Let's try this. Maybe it's by luck. Let's try BA. That's one way of obtaining the inverse of a matrix A. You simply solve a set of n linear equations where you essentially make the right hand side one of the identity vectors or unit vectors, and then you simply then put the solutions into a block row, and that's your inverse. So that means now you can find out the representation of B in this matrix because you found the inverse, right? What I would suggest is maybe try doing this procedure for a 3x3 matrix as well. Choose any matrix, just make sure it's full rank, and then do the same procedure to find out. Okay? Another procedure that I would also suggest is this. Here we had -2, 1, 1, 4. Form an augmented matrix where you put the identity matrix here. Okay? Try and convert this to the reduced row echelon form. Right? That means you just don't do the Gaussian elimination to make the numbers below the pivot 0. You then go back and make everything above the pivot 0, and you normalize the pivots so that the pivots will become 1. If you do that procedure, right, and you do the same operations on this side, right, what will happen is this section will get converted to I, and this section will get converted to A inverse. This you can verify yourself. All right, okay, that's all. We'll continue this tomorrow.